This is a lesson on p-values and what p-values are. First of all, a p-value, which is also called a significance level, is the probability that when HO is true, I would get a value as unusual as the one I got, or perhaps even more unusual. It says it's the probability, assuming HO is true, of observing a value of the test statistic that's at least as contradictory to HO and therefore supportive of HA is the one that you got from the sample. That sounds a little confusing. I think when you see it in practice it won't be. Here are the steps for figuring out the p-value. First of all, figure out the test statistic, which right now is the z statistic. We haven't done t statistics yet. If the test is one-tailed, the p-value is equal to the tail beyond z. If it's two-tailed, the p-value is equal to twice the area beyond the z. Now what does that mean? Well, if it's one-tailed, it means I'm looking at this. So the p-value would either be that shaded area or this shaded area. If it's two-tailed, that means we have a test that looks like this. So if this was my z statistic, it's this area or this area. A two-tailed test comes when you have a not equal to sign in HA. A one-tailed test is either a greater than or less than. And then the p-value will help you decide whether or not to reject HO. The alpha level is the largest p-value that you're willing to tolerate. If the observed significance level, the p-value, is less than or equal to the chosen value of alpha, then we'll reject. I call the alpha level the definition of weird. It's how weird you're willing to accept. A small p-value means there's lots and lots of evidence against HO. A large p-value means there's very little evidence against HO. We're always looking for evidence against HO. A small p-value means it's really unlikely that HO could be true and I'd still get this little value that I got. This value that's way far away from what I thought the original mu was. Let's see how this works. Again, the p-value is your definition of weird, and if your alpha level is your definition of weird, and if your p-value is less than or equal to that, we'll reject HO. So, example 1, if a hypothesis test said that alpha was 0.05, would I reject HO in part A? No, because that's bigger. Part B? No. Yes, no. Part C? Yes. Because there my p-value is less than alpha. How about D? Yes. E? No. F? Yes. What if I added G? 0.05. Yes. If my p-value equals my alpha level, I'm going to reject HO. Alright, how about this? Same idea. These are easy. It's just also easy to screw up. So I'm going to reject HO if my p-value is less than or equal to my alpha level. Just be careful not to get those backwards. Continuing with number 3, it says in a test of HO where mu equals 100, so here's 100, and the alternative is a one-sided greater than test, one-sided greater than, it says we came up with a z test statistic of 2.26. That means in terms of z, this is 2.26. When that is 0, when I standardize according to 100, I get a z test statistic of 2.26. Find the p-value of the test. So on my pink chart, I look up 2.26, and remember the pink chart shows me the area to the left, so I have to subtract that from 1. Or you can use your normal CDF, and you get the likelihood of getting a z-test statistic above 2.26 is 0.0119. That's my p-value. Number 4 is a similar problem. It says again that the original belief was that the mean was 100. That's if I look at it in terms of x. But now I have a two-sided test. So I have this area and this area. Well, what if the z-test statistic was 2.08? Then this over here would be negative 2.08 because it's symmetric. How likely is it that I would get something out there? Well, that's this and this are the same area. So if I take 2 times the probability of getting a z greater than 2.08, I end up with, look it up, do the normal CDF. Don't forget to multiply it by 2. And when I look that up on the pink chart and double it, I get 0.03753. Number 5, a less than case, just trying to get you used to each one of these cases. Be sure you're looking these up or using your normal CDF, because if you're not, you're just trusting me and I already know how to do it. Notice I sometimes put the X and the Z on here because all the Z is a restructuring of the number line. So now I want to know what's the probability I'd get a Z less than negative 1.11, and when I look that up I get 0.1335. That's the p-value. If my alpha level was that or something bigger, I would reject HO. Alright, let's look at number 6. Number 6 takes it a little bit further, and first I want to make a change. Instead of S right here, I want to change that to sigma. So sigma is 3.3. I draw a picture. The mean here is 50. I've got a one-sided greater than test because HA says mu is bigger than 50. And now I've got n equals 100, x bar equals 50.5, and sigma equals 3.3. Now it says find the p-value. So to find the p-value, I need to standardize it. I want to know the probability I would get an x bar bigger than 50.5. So I standardize that. 50.5 minus 50 over 3.3 divided by the square root of n. Try that on your calculator. And then when I look that up on my pink chart, I get 0.064867. That's from the calculator. Pink chart would be close to that. Now, since it asked me to interpret the p-value, I've got to make a determination if this is small or big, and that determination is given by alpha. Since I wasn't given an alpha, I'll make one up, and I'll say at alpha equals 0.05, my p-value is bigger than that, so I fail to reject HO in favor of HA. And therefore I continue to believe the original mu. If I had some context for what mu meant, I would say the average number of CDs sold by Hastings in a week is 50, or whatever it was. Okay, we got a couple more examples here. I'm going to give you a second to set up number 7 with the correction again that we're going to use sigma equals 2.1 instead of S. So we've got a test of HO where mu is 10 against HA, mu is not equal to 10. The sample data, n equals 50 observations, yielded a mean of 9.5, and we know sigma is 2.1. Find and interpret the p-value of the test. So I'm going to give you a second. I want you to draw a picture and write the question, which is basically this step that we did right up here, the very first thing. Okay. You got a picture. The middle of that picture is 10. I should be writing the standard deviation on here, which is 2.1 over the square root of 50. I suppose I should do that up here too. This was 3.3 over the square root of 100. I've got a two-sided test, so I have this and this, two-sided test. And so now I write the question. What's the probability that I would get an X bar? Now 9.5 is down here. So what's the probability I'd get an X bar less than or equal to 9.5? And I know, since it's a two-sided test, I need to double that. So that's 2 times the probability that Z is less than or equal to 9.5 minus 10 over 2.1 divided by the square root of 50. And you type all that stuff into your calculator, and you should get negative 1.68, which means in terms of Z, this is negative 1.68, and this is 0. The upper critical value would be 1.68, and in terms of X, this upper critical value would be 10.5. And the reason for that is because these distances are the same. The distance here is the same as the distance here. And so if this is 0.5, then this one also has to be 0.5. Continuing and looking that up on my pink chart or using the calculator, you get 2 times 0.04613, which when doubled gives me 0.09226. Probably in the spirit of number 6, I might fail to reject it, but I'm going to change this one a little bit, and I'm going to get a bigger alpha level. In particular, I'm going to say, what if alpha was 0.1? Well, now that p-value is less than that. So I'll say, since the p-value is so small, at least compared to the alpha level, and I'll go ahead and write that in here, that the p is this. That way, if somebody else doesn't think it's that small, they can change the conclusion around to meet whatever they define alpha to be. So since my p-value is so small, I reject HO in favor of HA. What does that mean? That means I no longer believe that mu equals 10, but I now think mu is not equal to 10. And again, if I knew what mu was, I would put that in there in context in the problem. Continuing now with number 8. The problem says a new blood pressure drug is advertised to reduce, after 1 week, a patient's blood pressure an average of 10 units. Blood pressure reductions were recorded for 37 patients. The mean was 8.7, and we're going to treat 5.1 as sigma. Do the data appear to contradict? Contradict, telling me it's a two-sided test. So it doesn't say is it more than they said or less than they said. We just want to know if it was different. Find the p-value, and are there any levels of alpha that you would reject for? So setting up HO, mu is 10, HA, mu is not 10, and we've got to define mu. having a hard time drawing a mu, where mu is the average reduction in blood pressure after 1 week. Anytime you use a letter like mu, you need to define it. Now I don't have to redefine sigma because sigma is understood to be the standard deviation of whatever you said mu was. So now when I write my givens, I have that x bar was 8.7, sigma was 5.1, and n is 37. On my picture, the middle of this is 10, like my original mu. It's a two-sided test, so those areas will add to give me my p-value. This is 8.7. That's 1.3 below 10. I just get that by subtracting. So 1.3 above 10 would tell me that's 11.3. And then this standard deviation is 5.1 divided by the square root of 37. So now I want to find 2 times the probability I'd get an x bar less than or equal to 8.7. Again, 2 times, because really it's the probability x bar is less than 8.7 plus the probability x bar is greater than 11.3. But I know those two areas are symmetric, so I could just take 2 times one of them. Standardize 8.7 minus the mean over the standard deviation. And so now I'm going to take the calculator out, figure out what all that jazz gives me. And you can continue along through this on your pink chart or on your calculator. Now that p-value is pretty high, but the question said find the p-value and then tell me what levels of alpha you would reject HO for. Well, if alpha is that number or bigger, I'm going to reject. So I'll write if alpha is greater than or equal to 0.1210, I will reject HO in favor of HA. That is, I will no longer believe the true average reduction in blood pressure after 1 week is 10 units, but that it is something different. Now be careful here. Just because the x bar we got was less than mu, our original HA was that mu wasn't 10. So when we reject HO, we go with HA, that it's not 10, that it's something different. We don't necessarily pick sides unless that was part of our original question. If you need to pause this and catch up and check all your numbers, do that. Otherwise, let's move on to number 9. The manufacturer of an over-the-counter pain reliever claims the product brings pain relief to headache sufferers in less than 3.5 minutes on average. In order to make this claim in television networks, the manufacturer was required by a particular TV station to present statistical evidence to support the claim. The manufacturer reported a random sample of 50 headache sufferers with an X bar of 3.3, and again we'll say sigma is 66 seconds. Let's change this number right here, this 3.3. Let's change it to 3.7. And I'll tell you why in just a minute, but let's change it and make it a little bit easier question, or a little bit more reasonable question here. Test A says, or question A says, do a hypothesis test with alpha is 0.05. B says, report the p-value. And then C, kind of talk about p-values for a second and see if you understand them. So HO says that mu is 3.5 and HA mu is greater than 3.5. And the reason I picked greater than is because if the powder works faster, the pain relief works faster than 3.5 minutes, I don't think anybody's going to complain. And so when this original question said 3.3, I think it's unlikely that anybody will care if it worked faster than advertised. I also need to define mu, since I used a mu, where mu is the average relief time in minutes. Write all my givens. N was 50, X bar was 3.7, sigma was 66. 3.7 minutes and 66 seconds. So 66 seconds, 66 divided by 60, that's 1.1 minutes. Can't believe I would do that to you. Draw me a picture. 3.5, one-sided test, 3.7 up here, and this is 1.1 divided by the square root of 50. Again, when I standardize, that 3.5 is going to become 0. Let's see how that works. This is the probability. X bar is greater than or equal to 3.7. So that C is greater than or equal to 3.7 minus the mean divided by the standard error of the mean. I'm going to use my calculator. That gives me 1.2856. So this value over here on my graph is 1.2856. That's the Z test statistic for an X bar of 3.7. Now when I use my pink chart or my calculator, I get that my p-value is 0.09928. Again, this problem gave me an alpha level. It told me that alpha was 0.05. So at the alpha equals 0.05 level, I fail to reject HO in favor of HA. Therefore, I continue to believe the average relief time is 3.5 minutes. In other words, while the average relief time might not be exactly 3.5 minutes, this sample of 50 people didn't provide me enough evidence to reject the manufacturer's claim. And part C says talk about p-values. Well, in general, smaller p-values make it much less likely that HO is factual. Well, generally speaking, larger p-values then make it more plausible for the original HO to be believed. So larger p-values mean an X bar like we got is more reasonable, or is more plausible with HO being true. A small p-value is evidence against HO. or against the manufacturer's claim. So hopefully this helps clear up some of the stuff about p-values and alpha levels and all the steps that I'd like to see. I think all these things that I'm writing on here are valuable and beneficial to correctly answering and analyzing a question like this.